Imagine a car battery that charges in just 8 minutes, lasts millions of miles, and still manages to maintain nearly its full capacity as if nothing had happened. It sounds like the stuff of science fiction, but that's exactly the kind of revolution Tesla is quietly engineering behind the scenes. The company has managed to reinvent aluminum-ion batteries, a type that until recently was viewed with suspicion by experts. And that's no exaggeration. The data speaks for itself. With a new three-dimensional honeycomb structure and cells up to 80% thinner, energy density has jumped to 320 Wh per kilogram, enough to put many a lithium-ion car to shame. This density, which previously limited vehicle range to a modest 250 or 300 miles, now delivers up to 450 miles on a single charge, equivalent to over 720 kilometers. All this in a 75 kWh pack, without increasing weight or volume. This feat was only possible thanks to an engineering leap. The 3D stacking of cells in ultra-thin layers, just 10 nanometers thick, allows for better internal space utilization. It's as if everything inside has been shrunk to accommodate more energy without taking up more space. The result is that, for the first time, an aluminum battery truly competes head-to-head with market leaders. But the secret doesn't stop with the structure. Graphene, already a powerful material by nature, has been given a clever boost. A nanopolymer coating has been added to the anode to better distribute ions across the surface. Previously, only 65% of the total area was used for energy storage. With this new layer, that utilization jumps to 95%. In simple terms, it's as if the battery has discovered a new way to store energy in places that were previously empty. The impact on overall performance is dramatic, and it's not just about power, but about true efficiency. The charging speed is also jaw-dropping. These new aluminum-ion batteries reach 100% charge in just 8 minutes, without overheating or risking fire. Unlike lithium, aluminum doesn't spontaneously combust if it fails. This means less risk of explosion in accidents and more peace of mind for drivers. This thermal safety, combined with the recharging speed, creates an experience that closely resembles what gasoline-powered car drivers are used to. Stop, fill up, and go. The difference is that now, filling is done with a cable and without the smell of gasoline in the air. Another point that often raises questions is durability. And once again, the battery surprises. We're talking about a life cycle of 5 million miles, with 89% of original capacity preserved. To put this in perspective, it's as if the same battery pack lasted through multiple generations of cars without needing to be replaced. This longevity completely changes the logic of maintenance and component replacement in electric vehicles. The car owner simply forgets the battery exists. It keeps working, like a tireless heart, mile after mile, trip after trip. Until now, one of the biggest obstacles to aluminum batteries was precisely this: their low energy density compared to lithium. They couldn't deliver satisfactory range and were therefore ignored in the automotive sector. But with this new formula, that barrier has fallen. With 320 Wh, Tesla not only meets but surpasses what many considered the technical limit of the technology. And most importantly, without compromising pack size, car weight, or passenger safety. This is a game changer, and competitors know it. Of course, achieving this leap required a series of innovations. The cell design, the intelligent stacking, the change in anode coating material, and even the reduction of voids between cells were all designed with a single goal in mind: to do more with less. Tesla not only packed more energy into a similarly sized box, but it did so with a cheaper, safer, and more recyclable material than lithium. And while many still wonder if these batteries actually work, internal data shows they're already in the advanced testing phase. While aluminum is making strides in performance, sodium has been surprising where almost no one expected: in cost. Tesla has managed to bring down the price of sodium-ion batteries to only $11 per kilowatt-hour, a figure that seemed impossible even to the most optimistic analysts. This figure was achieved by abandoning conventional sodium extraction in salt mines, which cost around $500 per ton, and switching to recycled industrial waste, specifically sodium extracted from glass and chemical industry byproducts, at a fraction of the cost. This alone changed the economics of the technology. But it didn't stop there. Instead of traditional 800 C furnaces, which consumed 50 kilojoules of energy per ton of sodium processed, Tesla implemented a low-temperature extraction system. Using an innovative organometallic catalyst, the process now occurs at just 200 C, consuming only 15 kilojoules per ton. This drastic change represents a 70% savings in the refinement stage, something that not only reduces the final cost of the battery, but also makes the entire production chain more sustainable. Less energy, fewer pollutants, more efficiency. All of this on a large scale. This new process paved the way for something even engineers considered unlikely. A 75 kilowatt pack can now be manufactured for about $2,200, against the absurdities 11,400 of conventional lithium-ion batteries. This $10,000 difference is the kind of advantage that changes the entire market. After all, if the biggest cost of an electric car has always been the battery, reducing that cost by 90% is practically like redesigning the car from scratch, only with the same performance. And the most impressive thing is that this radical change was accompanied by improvements in the battery's technical performance. Sodium's biggest weakness has always been its energy density. That is, how much energy fits into each kilogram of the battery. For a long time, it was between $120 and $160, far from lithium's 250 to 300 kg. But now, with new electrode stacking techniques inspired by aluminum batteries, sodium-ion density has jumped to 275 Wh/kg. This not only puts sodium almost on par with lithium, but also surpasses BYD's famous Blade battery, used even in Model Ys manufactured in Germany. A leap that changes everything. In addition to being denser and cheaper, the new sodium battery also proves to be incredibly durable. Its durability reaches 15,000 recharge cycles, which is equivalent to decades of continuous use. And even under extreme temperatures, such as 30 degrees C, she keeps 90% of original capacity, a number that dismantles the biggest argument against sodium, its supposed instability. While lithium loses up to 40% of its efficiency in extreme cold, sodium barely feels the impact. This makes it the ideal candidate for delivery fleets, cold regions, or any application where reliability is critical. This scenario puts Tesla in a very uncomfortable position for its competitors, especially BYD, which had been dominating the market with its cheap batteries. Now, Tesla delivers something even cheaper, with more quality and superior durability, and everything indicates that the process will continue to evolve. Competitive pressure is inevitable, especially since advances aren't limited to laboratories. Tesla's sodium batteries are already in the industrial testing phase, and pre-commercial production is underway, meaning that large-scale adoption is a matter of just a few months away. If sodium was previously seen as a low-performance alternative with limited use, it now emerges as a powerful strategic weapon. And the secret lies precisely in how Tesla changed the game. Instead of trying to copy lithium, the company explored what sodium has to offer: abundance, stability, and versatility. It adapted its processes, used the materials intelligence applied to aluminum batteries, and created something new that works well and costs little. This makes sodium not just an option, but a central piece in the electric future that is emerging. With aluminum's performance on one side and sodium's aggressive cost on the other, Tesla now needs to decide where each technology makes the most sense. And this decision won't just be technical, but strategic. After all, what's seen in the labs is about to hit the streets. And the first models chosen to carry these new batteries promise to shake up the market in ways no one imagined. The decision to use each battery type wasn't made by chance. Within Tesla's plans, sodium-ion and aluminum-ion fulfill very different roles, designed to maximize cost and performance depending on each vehicle's use. For current models, such as the Model 3 and Model Y, the company doesn't intend to immediately replace LFP batteries, at least not until 2027. What we're seeing is a well-calculated strategy. Maintain established lines with stable chemistry while simultaneously introducing new technologies into new products to test their acceptance and industrial scale without changing what's already working. The clearest example of this strategy is in the future Tesla Robovan, scheduled for release in 2027. This model, geared toward urban deliveries and continuous service, has different requirements than a passenger car. It needs to carry heavy loads, operate for long hours, and withstand extreme temperatures without compromising range. Here, sodium-ion makes perfect sense. Its low cost drastically reduces the vehicle's final price, and its stability in cold or hot climates ensures predictable performance. Tesla appears to want to transform this van into a sort of electric workhorse for commercial fleets. Meanwhile, aluminum-ion targets a completely different segment. Its high energy density and fast charging capability make it ideal for long-distance, high-performance vehicles, where every mile of range and every minute of recharging matter. This is where projects like Tesla Semi, which requires robust, safe batteries with enormous capacity to travel thousands of kilometers without significant loss of performance. Aluminum is, therefore, the company's choice for the top of the chain of electric vehicles. But the most interesting point of this transition is in the Model 2, scheduled for the third quarter of 2026. This car is seen as the first major public test of both technologies simultaneously. Tesla plans to offer different versions of the same model, one with an aluminum-ion battery aimed at those seeking maximum range and performance, and another with a sodium-ion battery, more affordable and focused on cost-effectiveness. This modular approach not only broadens the car's target audience, but also allows the company to compare, in practice, how the two chemistries behave in drivers' daily lives. This move to debut technologies in a completely new model also serves to avoid image and production risks. Instead of modifying already established vehicles, such as the Model 3, Tesla chooses a neutral field to test aluminum and sodium with more freedom. This allows room for fine-tuning before expanding to other models in the lineup. If performance and acceptance are positive, these batteries are likely to gradually replace current chemistries, redefining not only prices, but also the standard for range and durability in the electric vehicle sector. Another important factor is the timeline. According to leaks from Q3 2025, production lines for aluminum batteries could be ready in 10 to 12 months, with an initial estimated capacity of 80 GWh per year at the Nevada and Texas Gigafactories. Sodium batteries are being tested at Giga Shanghai, in partnership with materials companies like CL, and should enter mass production even before aluminum, with the transfer to Giga Texas scheduled for December 2025. This timeline gap indicates that the sodium versions of the Model 2 could reach the market sooner. This difference in timing between one technology and the other also reflects the complexity of production. Aluminum requires more precise processes and lines adapted to its ultra-thin cells, while sodium is more flexible and cheaper to implement. This means that, despite being a revolutionary technology, aluminum may start on a smaller scale, aimed at premium models, while sodium arrives first to democratize access to the Model 2, a contrast that could create a clear divide between entry-level and high-performance models within Tesla's portfolio. With these strategic choices, the company not only positions its new batteries intelligently, but also builds a narrative of continuous innovation that reinforces its industry leadership. Instead of offering a one-size-fits-all technology, it diversifies, combines, and adapts its innovations to real market needs. This multifaceted approach is what could make the Model 2's arrival a game-changer for the entire industry, setting a standard that other manufacturers will have to race to achieve. With the implementation of the new chemistries defined, the next step was to develop a production plan capable of sustaining aggressive pricing without compromising scale. Tesla knew that creating a better battery wasn't enough. It needed to mass-produce it at overwhelmingly lower costs than had been the case previously. And that's where the partnership with Redwood Materials, a key piece in the radical cut in aluminum battery prices. By recycling aluminum with up to 95% less energy consumption in relation to the production of virgin material, the company managed to drastically reduce the environmental and financial impact of the process. The result was a dramatic drop in manufacturing costs. The price per kilowatt-hour of aluminum batteries plummeted from $60 for just $36, a number that completely changes the math of an electric car. This allowed the aluminum battery version of the Model 2 to be designed to cost between $2,200 and $2,400 for the battery alone, a previously unthinkable value for performance packs with 450 miles of range. And with this margin, the final price of the car was set at $19,000, targeting the premium compact segment directly and challenging much more expensive competitor models. On the other side of the spectrum, the Model 2 with a sodium battery is even more aggressive. With a battery cost of just $1,200, the entry-level model will be released by less than $17,000, targeting the mass market in the United States and Asia. And this isn't a limited edition or a future concept. It's a plan with a set date. Large-scale production of the sodium versions begins in the second quarter of 2026, with 500,000 units expected in the first batch Tesla wants volume, and everything indicates that it will achieve it. The difference between the two models goes far beyond price. The aluminum model is aimed at drivers who need maximum range and ultra-fast charging, while the sodium model is positioned as a robust, efficient, and incredibly affordable urban vehicle. Both share the same basic structure, but have distinct purposes. This clear separation of target audiences allows the company to optimize its production, avoid wasting resources, and, at the same time, serve two distinct markets with a single base model. A bold but extremely well-thought-out strategy. To meet this colossal demand, Tesla is restructuring its Gigafactories, Giga, Nevada, and 2 Giga Texas Air being equipped with new dry electrode lines, specifically adapted to handle aluminum materials. Giga Shanghai is leading the sodium tests and, in partnership with CL, is validating the low-cost processes that will later be applied in the United States. The forecast is that Giga Texas assumed the mass production of sodium batteries from December 2025, with a capacity of 100 gigawatt-hours. In addition to factories, Tesla is also investing heavily in automation. The new chassis assembly system, for example, can produce a car frame every 5 seconds, an engineering feat that drastically reduces assembly times. When this speed is combined with the manufacturing speed of the new batteries and the optimized logistics of local supply chains, the wait time between order and delivery drops from months to weeks. This is the industrialization of efficiency applied directly to the end consumer. With this accelerated production model, Tesla expects to deliver the first Model 2s in Q2 and Q3 by 2026, with simultaneous distribution to the United States, Europe, and Asia. This global scale at launch is rare in the automotive industry, which typically limits initial production to local markets. But the investment in two distinct chemistries, with dedicated lines and already optimized costs, allows for this ambitious leap. And all this without relying on scarce materials or vulnerable supply routes, which closes the production cycle with independence and stability. Ultimately, what Tesla is doing is redefining not only the electric car, but the very logic of how it's manufactured, priced, and delivered. By combining materials, innovation, industrial intelligence, and strategic planning, the company charts a path where low cost and high performance are no longer opposites.